All right, physics students, today I'm gonna just go ahead and get you started on some of this homework here. I tried to do it during class, but the video was kind of messed up, so I'm just gonna go ahead and do this again. So number one on page 232 says, what must be the distance between 2.800 kilogram balls if the magnitude of the gravitational force between them is equal to that in sample problem C? So I have two masses, M1 and M2, and they are each 0.800 kilograms. And the force from sample problem C is 8.92 times 10 to the minus 11th newtons. And the question is, how far apart are these two masses? Well, if I draw them here, here's M1, here's M2. The question is, what is R? How far are these two apart? And I should actually draw that to the center of each one, but I'm going to use Newton's universal law of gravitation. F sub g equals capital G M1 M2 over R squared. And I want to solve for R. So I'm going to multiply both sides by R squared to get R out of the denominator. So that cancels these two. I want to get rid of F sub g. And so let's just rewrite this to get rid of some of the clutter. I'm going to take the square root of both sides. So R equals the square root of G M1 M2 over F sub G. And then you will plug those numbers in and find an answer for R. Now, one of the things I mentioned yesterday, or not yesterday, in class, was how you enter these numbers into your calculator. If I'm entering a number like this into my calculator, I can do it in one of two ways. I can type in 8.92, then I hit the times button, and then I hit 10, and then I hit the caret button, and then I put in -11. If you do it this way, you have to make sure that you put parentheses around that so that the calculator understands that that is one number. The way I do it on the calculator is I go 8.92, I then hit the EE button, which brings up a little E, and then I type in -11. The calculator automatically knows that this is one number. I don't need to use parentheses here. But if you do it this way, you need to put those parentheses around. Otherwise, you screw up your answer, particularly if that's in the bottom of your math here. So, all right, let's go to number two. Number two, Mars has a mass of about 6.4 times 10 to the 23rd kilograms, and its moon Phobos has a mass of about 9.6 times 10 to the 15th kilograms. If the magnitude of the gravitational force between the two bodies is 4.6 times 10 to the 15th, how far apart are Mars and Phobos? So what do I know? I have two masses again. I have the mass of Mars, which I'm going to call MM instead of M1. I can call it M1 if I want. But that's going to be 9.6 times 10 to the 15th kilograms. I'm sorry, that's incorrect. That's the mass of Phobos. Mass of Mars is 6.4 times 10 to the 23rd kilograms, about one order of magnitude smaller than the Earth. So about it's about 10% the size. I shouldn't say 10%. It is 10% the mass of the Earth. Am I doing that math right? Anyway, point being, if the magnitude of the gravitational force between the two bodies is 4.6 times 10 to the 15th, how far apart are Mars and Phobos? So once again, we're looking for R. You're going to use that same equation and same process to get that equation that you did before. All right, and then number three, there are three parts to this one, and you can, I'm just going to go through number one, and then you can, do the rest obviously on your own. So number three, find the magnitude of the gravitational force So we're looking for F sub G. A 66.5 kilogram person. Mass of the person is 66.5 kilograms. And then we want to know what is the force between that person when he is on Earth, when on Mars, and when on Pluto. So in order to find out what the force is between that person and the Earth, we need to know the mass of the Earth. And the mass of the Earth is 5.97 times 10 to the 24th kilograms. All right, and then the the radius of the Earth, r, is 6.38 times 10 to the 6th meters. Now, why do we care what the radius of the Earth is? The reason we care about that is when you are standing on the Earth, the distance between you and the planet is not zero touching the surface. We treat all masses as if their mass is concentrated at their center. So how far away are you from the center? Well, that's the radius of the Earth. This is 6.38 times 10 to the 6th meters. And that's the distance we care about. So to find F sub G here, just use the universal law, capital G, M, person, M, Earth, over R squared. And then we go 6.67 times 10 to the minus 11th. Again, you don't have to have that memorized. You can look that up every time. And then it's the mass of the person is 66.5 kilograms. And the mass of the Earth is 5.97 times 10 to the 24th kilograms, all over 6.38 times 10 to the 6th meters squared. And you can finish that one off and then do B and C. Or number 1 on 237. Explain how the force of gravity keeps a satellite in orbit. Okay, that's a conceptual question. I'm not going to go through that one. Number 2, is there a gravitational force between two students? Explain why we don't observe that. Number 3, Earth has a mass of 5.97 times 10 to the 24th and a radius of 6.38 times 10 to the 6th, while Saturn has a mass of 5.68 times 10 to the 26th and a radius of 6.03 times 10 to the 7th. Find the weight of a 65 kilogram person at the following locations: A, on the surface of the Earth; B, 1,000 kilometers above the surface; C, on the surface of Saturn; D, 1,000 kilometers above the surface of Saturn. Okay, so we have 4 situations. Surface of Earth, 1,000 kilometers above Earth, the surface of Saturn, and 1,000 kilometers above Saturn. And again, we're finding the weight of that person. So the mass of the person, MP, is 65.0 kilograms. All right, mass of the Earth is 5.97 times 10 to the 24th kilograms. That's true here as well. Mass of Saturn is 5.68 times 10 to the 26th. Again, 100 times bigger than, 100 times more massive than Earth. The radius here for Earth is 6.38 times 10 to the 6th meters. 1,000 meters above that, though, R is, it's times 10 to the 6th. So that's going to be, or plus times 10 to the 6th. So that's going to be 7.38 times 10 to the 6th meters. Radius of Saturn is 6.03 times 10 to the 7th meters. So 10 times bigger. 10 times bigger radius. And 1,000 kilometers above that, or 1,000,000 meters, would be 6.13 times 10 to the 7th meters. Okay, so you can see, hopefully, again, I'm not going to do every one of these, but you're just going to basically, again, go through F equals M1, M2 over capital G over R squared. And you're just going to change different R's for each situation. Notice that what you should find is that going 1,000 kilometers above the Earth will have more of an effect than going 1,000 kilometers above the surface of Saturn, because it's a smaller percentage of Saturn's radius. So it's not very much compared to what it was. So anyway, you'll have 4 answers for FG here, and you compare what happens. And then finally, number 5, it says, find the mass of the Earth. We just found out what capital G is. Use the value of G and an approximate value for Earth's radius to find an approximation for Earth's mass. So here's how you would go about that. We know that the force of gravity on Earth is capital G times M1, and let's call it U. So we'll just call you M1, M2, which is the M of the Earth, over how far away you are from the Earth, or rather the center of the Earth. We know that R equals 6.38 times 10 to the 6th meters. Okay. Now, we don't know the mass of the Earth. That's what we're trying to find. But we do know this. Now, do we know the force of gravity on U? Well, the force of gravity on U is going to be your mass, M1, times G. All right. So this is equal to this. So let's set them equal. So we're going to go capital G, M1, M Earth over R squared equals M1 times little g. All right, well, M1 is in both parts, right? And it's not being added or subtracted, so we can cancel that. All right, I want to find the mass of the Earth. So let's get rid of G. Let's divide both sides by capital G. And let's multiply both sides by R squared. Now, I can solve for the mass of the Earth, and that's going to be little g R squared over capital G. And again, from there, you can just plug and chug. All right, that's the homework.